In this chapter, we'll discuss some architectural use cases for GraphQL, as well as some major components that you'll find in all GraphQL infrastructures. One thing to note in the beginning is that GraphQL itself has only been released as a specification. This means that GraphQL is in fact not more than a long document that describes in detail how a GraphQL server has to behave, meaning what kinds of requests it should accept and what the response format for these requests has to look like. You can read the specification under the URL that's displayed on the bottom of this slide. If you want to use GraphQL in a project, you'll have to go and build the GraphQL server yourself. You can do that in any programming language of your choice. And you can use one of the available reference implementations for it. But you can also use a service like GraphQL that provides a powerful GraphQL server out of the box. We will now walk you through 3 common architectural use cases for GraphQL. The first one is a GraphQL server with a connected database. This is quite a simple setup that we'll discuss in the next section. Then we have a GraphQL server that is a thin layer in front of a number of third-party or legacy systems and integrates these systems through a single GraphQL API. The third is a hybrid approach of a connected database and third-party or legacy systems that can all be accessed through the same GraphQL API. All these 3 architectures represent major use cases of GraphQL and demonstrate the flexibility in terms of the context where GraphQL can be used. Let's first talk about the use case of a GraphQL server with a connected database. This architecture will be the most common for greenfield projects. In the setup, you have a single web server that implements the GraphQL specification. When a query arrives at the GraphQL server, the server reads the query's payload and fetches the required information from the database. This is called resolving the query. It then constructs the response object as described in the official specification and returns it to the client. Here you see an illustration of this use case where a client is communicating with a single GraphQL server over the web. It's important to note that GraphQL is actually transport layer agnostic. This means it can potentially be used with any available network protocol. So it is definitely possible to implement a GraphQL server based on TCP, WebSockets, or any other transport. GraphQL also doesn't care about the database or the format that is used to store the data. You could use a SQL database like AWS Aurora or a NoSQL database like MongoDB. Another major use case for GraphQL is the integration of multiple existing systems behind a single coherent GraphQL API. This is particularly compelling for companies with legacy infrastructures and many different APIs that have grown over the years and now impose a high maintenance burden. One major problem with these kinds of legacy systems is that they make it practically impossible to build innovative products that need access to multiple systems. In that context, GraphQL can be used to unify these existing systems and hide their complexity behind a nice GraphQL API. This way, new client applications can be developed that simply talk to the GraphQL server to fetch the data they need. The server is then responsible to make sure it fetches the data from the existing systems and packages it up in the GraphQL response format. Just like in the previous architecture where the GraphQL server didn't care about the database being used, this time it doesn't care about the data sources that it needs to fetch the data that's needed to resolve a query. Here we see the illustration of such a system where the GraphQL server acts as the integration layer for legacy systems, existing microservices, and third-party APIs. And finally, it's also possible to combine the 2 approaches and build a GraphQL server that has a connected database but still talks to legacy or third-party systems. In this architecture, when a query is received by the server will resolve it and either retrieve the required data from the connected database or from the integrated APIs. But how do we actually gain this flexibility with GraphQL? How is it that it's such a great fit for these very different kinds of use cases? The key to understanding how GraphQL is able to cope with all these different environments is the concept of a resolver function. As you learned in the previous chapter, the payload of a GraphQL query or mutation consists of a set of fields. In the GraphQL server implementation, each of these fields actually corresponds to exactly one function that's called a resolver. The sole purpose of a resolver function is to fetch the data for its corresponding field. Let's now consider the example of a query that is sent to a GraphQL server and think about the resolver functions that are required to properly respond to that query. Here, we send a query to ask for the user that's identified by a particular ID. In the payload of the query, we specify the information that we'd like to have returned by the server. In our case, that's the user's name, as well as their first 5 friends, of which we are requesting the name as well as the age. The first resolver that would have to be implemented is for the root field of the query. In that case, that is the user field. The resolver function for the user field takes a required ID as an argument and potentially returns a user instance. The return type is nullable since we don't know that the user with the provided ID actually exists. Notice that the function signatures are just pseudocode to illustrate the idea behind resolver functions. The actual function signatures of your resolvers that you write for your GraphQL server implementation might differ depending on your context. We then can add a resolver function for the name field. Name is a field on the user type and doesn't take any external arguments that can be provided in a query. However, in order to be able to find the name of a user, the server needs to know which user that is. The resolver function thus takes a user as an implicit argument. The return type of this resolver is a non-nullable string, which corresponds to the type of the name field in the GraphQL schema. Next, we can add the resolver function for the age field. That's analogous to the name field, except that it returns an int instead of a string. And finally, the friends field in the query payload can be resolved by a corresponding function that takes an optional parameter called first that can be provided in a query, as well as the implicit user argument, since friends also is a field on the user type and the server needs to know whose friends it should fetch. This function returns a list of users. The last concept that we'll cover in this chapter is the concept of a GraphQL client. GraphQL is a particularly great technology for front-end developers, since it completely eliminates many of the inconveniences and shortcomings that are experienced with REST APIs, such as over and under fetching. Complexity is pushed to the server side, where powerful machines can take care of the heavy computation work. The client doesn't have to know where the data that it fetches is actually coming from, and can use a single coherent and flexible API. This provides an opportunity to build new abstractions on the front end to make it even easier for developers to interact with an API. Let's consider the major change that's introduced with GraphQL in going from a rather imperative data fetching approach to a purely declarative one. When fetching data from a REST API, most applications will have to go through the following steps. First, they have to construct and send the HTTP request, for example using the fetch function in JavaScript. Then they have to receive and parse the server response. The data that they parsed out of the response has to be stored locally, either simply in memory or maybe persisted. And finally, the data can be displayed in the UI. With the ideal declarative data fetching approach, on the other hand, a client shouldn't be doing more than the following 2 steps. First, it has to describe its data requirements, and then it can display the information in the UI. Everything that's in between should be handled by the GraphQL client. All the lower level networking tasks, as well as storing the data, should be abstracted away, and the declaration of data dependencies should be the dominant part in the data fetching process. This is precisely what GraphQL client libraries like Relay or Apollo will enable you to do. They provide the abstraction that you need to be able to focus on the important parts of your application rather than having to deal with the repetitive implementation of infrastructure and data fetching logic. You're now done with learning about the fundamentals of GraphQL and can choose whether you want to continue learning about more advanced GraphQL concepts